Okay, good afternoon, no-end growers. Thank you for coming in to listen to my presentation on object-oriented programming. What is it? Why is it? So, as I assume some of you know, I'm an adjunct computer information management instructor at Saddleback College. And I'm also an adjunct computer science instructor at Riverside City College. I am also the co-author with Ed Jordan of a book entitled Case Studies in Object-Oriented Analysis and Design. And you can tell I'm pointing my laser pointer at a screen and you can't see my laser pointer. I'll try to do better. So most of today's lecture is based on material in the object-oriented analysis and design case study book. So as you can see, I'm not sure how good the Zoom camera is, but as you can see, I am a very old man. As I tell my students, I am the only computer instructor whom they have today. In fact, I'm the only computer instructor whom they will ever have, who was born before the birth of the modern programmable digital computer, something called the ENIAC, Electronic Numerical Integrator and Computer, which was born in 1946, and I predate that. I have been working with computer technology my entire life. In fact, like many of the students I have in my computer programming classes, I started programming when I was in high school. So this is a picture of me in my high school electronics class. This would have been taken in about the year 1960. And that was at the time that I was programming an IBM 709 computer, a computer that looked something like this. A computer that fit in a room about the size of a basketball court. Most of this computer you can't see. I'm pointing over here to the right-hand side of the computer, which is mostly circuit boards, because actually this computer filled up this huge room with mostly circuit boards like this. So this circuit board is a little smaller than an 8.5 by 11 inch sheet of paper. And this circuit board stores 1 byte of data. The IBM 709 computer was capable of storing thousands of bytes of data. It was capable of performing thousands of operations per second. I walk around today with a different computer, my Pixel 5 phone, which I kind of have a love-hate relationship with, but that's another story for another lecture. This Pixel 5 phone has billions, is capable of storing billions of bytes of data and performing billions of operations per second. So over my lifetime, most of you, I'm sure, are familiar with Moore's Law. Moore's Law over my lifetime is represented by this logarithmic graph, starting about the year 1960, the IBM 709 computer, to my Pixel phone that I can hold in the palm of my hand today. Performance 1,000,000 times greater. There's another way of phrasing that I prefer to articulate, and that is, I am now holding in the palm of my hand a computer that's not merely 1,000,000 times faster than the IBM 709. It's equivalent to holding 1,000,000 of those computers in the palm of my hand. Now, if I were, this is a story, as those of you who are my students know, I tell on the first day of class. If I were to tell you that over my lifetime, a computer that occupied a room the size of a basketball court now fits in the palm of my hand, that would be amazing. But that's not what I'm saying. What I'm saying is 1 million of those computers now fit in the palm of my hand. And that's more than amazing. That's like mind-boggling. In my opinion, the advancement of computer technology over my lifetime has been one of humans' greatest achievements. I cannot think of another field of endeavor, anything, agricultural, industry, I don't know, anything you can think of, which over a single human lifetime has advanced as computer technology has advanced. And the scary part is, and indeed, you should be afraid, very afraid, this is only the beginning. But that's all fodder for another lecture. Let me move on. Here's another graph, which is as important for today's lecture and elsewhere as this picture of Moore's Law. This is a depiction of not very good drawing on my part of the cost of a programmer as a percent of the cost the programmer of the computer, the programmer is programming over my lifetime. So I began programming, quote, professionally. My first job out of college was as a programmer analyst at the Manned Spacecraft Center in Houston, Texas, on the Apollo project. And I remember when I got that job out of college, I was just blown away because it was a milestone salary in the mid-1960s. My salary as an entry-level programmer analyst on the Apollo project was $10,000 a year. The computer that I was programming cost over $1 million. So for my first job out of college, the cost of a programmer was approximately 1% the cost of the computer. As the years have gone by, consider this to be about current 2022, the cost of a programmer now is, let's say, roughly $100,000. And the cost of the computer that programmer is programming is roughly $1,000. 1% the cost of the programmer. So this 1% figure has flipped over my lifetime. The cost of the programmer, 1% the cost of the computer. The cost of the computer, 1% the cost of the programmer. That's not only interesting, but in fact, the reversal, in my opinion, the reversal of the cost of programmer and cost of computer has, in my opinion, been the driving force behind the development of software methodologies and programming paradigms. I'm going to make that argument somewhat coming up. In my opinion, there would be no need for object-oriented programming if programmers were cheap and computers were expensive. So even though I haven't said anything yet about what is object-oriented programming, in my opinion, object-oriented programming is inextricably bound up with the economics of programming. So let's move on. By the way, this amazing graph, which shows the, well, in fact, let me go to the first one. This amazing graph, the first of two amazing graphs, which shows how Moore's Law has evolved over my lifetime. And this amazing graph, which shows how the cost of programmer has reversed vis-a-vis the cost of computer. All of that happened over my lifetime due to a whole bunch of factors that brought us from then to now. And none of these are part of my lecture today, which is technically on object-oriented programming. However, I think it's useful if I bring up parenthetically just a few of the factors which, in my opinion, brought us from then to now. For example, electronics technology, the invention of the transistor, that circuit board with vacuum tubes, when it was, quote, the term was transistorized. Instead of storing 1 byte of data, stored 1,000 bytes of data. The development of material science and integrated circuits, and all of the support technologies that allowed fabrication of computer components with greater and greater densities, even such mundane things as dissipating heat. Another factor was the changing programmer demographic. Believe it or not, when I entered the industry in the mid-1960s, there were no computer science programs. Computer science programs hadn't been invented yet. I had a passion for computers, so I did what many other people who wanted to work in the computer field did. I went into engineering. Most of the people that I worked with had degrees in electrical engineering or in mathematics. I had a bachelor's degree in electrical engineering and a master's degree in mathematics. So I was in high demand to be a, quote, programmer, even though we never studied programming as a discipline. So the changing programmer demographic has brought us from then to now in ways that I won't elaborate. And then there was the birth of actual computer science programs. And that allowed bringing into this new field called computer science other disciplines aside from just engineering and mathematics. And then the applications of computer technology broadened greatly. Initially, the first computer, programmable digital computer, electronic numerical integrator computer, military purposes, various kinds of military calculations, trajectories, and so on and so forth. But now we're began to apply computer technology to very mundane business processes. And then the evolution of the business and industrial environments. More data being generated and collected. Processes which became sufficiently complicated that algorithms were developed. Let's thank Henry Ford for attempting to create an automated manufacturing process, which involved the development of all kinds of algorithms, invention of the flow chart, and so on, and spawning the need of some kind of processing technologies. And then, of course, there were the kids with computers. You know, those kids were so cute using these room-sized computers. And then they went and grew up and they became computer professionals, and they saw the world of computing completely different than their parents did. And of course, the evolution of the communication infrastructure, birth of the internet, and so much more. So you can consider this as just a bunch of parenthetic comments that brought us from then to now. Okay, I've been blathering on for a while. Let me talk about, in order to introduce the concept of object-oriented programming, I want to say a few words about how programming was done, back in the before times. And the typical way that you would approach a computer programming problem was with so-called top-down functional decomposition. By the way, later on in this presentation, I'll talk a little bit about an elevator control system from the object-oriented book. But if you wanted to create some kind of an elevator control system, you'd start scratching your head and ask yourself, okay, what's the highest level task that I have to perform in order to program and implement an elevator control system? Okay, well, manage elevators, okay, or control elevators. So that might be the top of a structure chart. And now what do I have to do if I'm going to manage or control elevators? Well, there might be a next level of software code, modules, subroutines, etc. Maybe to manage elevator movement. I don't know, maybe to monitor floor sensors. I don't know, maybe to monitor summons buttons, monitor, control, destination panel. And there's a whole bunch of things that might go into the second level of a top-down functional decomposition. Okay, well, now I want to control elevators. What do I have to do? Probably I have to control a motor. Probably I have to read a floor sensor or something like that. And eventually you work down, my apologies for continuing to use my laser pointer that you can't see. Eventually you work down from the highest level, control elevator, down to more and more finely and refined functions that bring you down to the primitive level, maybe functions that control individual buttons on an elevator. Top-down functional decomposition. That was the natural approach for programming computers in the early days, in the early stages. And the reason for that was that that paradigm was natural for computers, which were viewed as machines that did input, process, output. And it was also a very natural paradigm for the early programmers. So those of us who had a background in electrical engineering, well, lo and behold, that's how we built various kinds of electronic devices. You defined what the device would do, and then you asked yourself, okay, let's see, I want to create some kind, I don't know, let's be mundane, an AM radio, something like that. Okay, well, what do I have to build for an AM radio? Okay, I need RF amplifier stages, and then I need some kind of a super heterodyning circuit that converts that RF frequency into an intermediate frequency. Okay, what do I need? Okay, then I need something that actually demodulates the signal from the carrier. And then I need an audio amplifier so that people can actually hear the radio. So that's a functional decomposition of a radio. So it was natural for those programmers to view the world as top-down functional decomposition. It was also natural, by the way, for mathematicians, because mathematicians who were also programmers, they viewed programs like they viewed mathematical theorems. And so there was this kind of sense of input, process, output. The programmers would look at the mathematicians as programmers would look at the program as a theorem where you would start out with axioms or lemmas, and then step by step, you would execute an algorithm that was kind of like a mathematical proof. Until the program was done, QED was your output. So it was just a natural way for the early programmers to work. However, and I'm now about to give you a very important key point, all of this had to be implemented within the context of maximizing hardware performance. So remember, this is such a key point that I have to go back to the very beginning. Remember, I'm dealing with $1 million computer that stores 1 byte of data on a circuit board like this. And I only have thousands of these circuit boards, not millions, and certainly not billions. And so to implement top-down functional decomposition, I also had to implement that within the context of maximizing hardware performance. And that resulted in the creation of something that's referred to as spaghetti code. I was talking with a computer science student at Saddleback College, I don't know, last semester, whatever. And I asked him, well, do you have any idea what is spaghetti code? And he said, oh yeah, that's poorly written code. How sad that we have come to the point in computer science where spaghetti code is viewed as, quote, poorly written code. In fact, spaghetti code was masterfully written because all of these functional decomposition modules, they all had to be interconnected in ways that maximized hardware performance. So the reason that I'm going from this module all the way around over here to this module is because by doing that kind of a jump, I save 1 byte of information, 1 byte of data. And every byte counts. When I was a baby programmer at the Manned Spacecraft Center, one of the things you get to do when you're a new programmer is you get to take over maintenance of existing programs which have been developed by more senior programmers. And God bless him, Charlie M. Skillman. If he's alive today, he'd be in his hundreds. He created this program where, in order to save bytes, he declared variables where we would normally use literals in a program. So he had a variable called ONE, which was the value 1, and then he had another variable, TWO, which was the number 2, and another variable, THREE, which is the number 3, and so on. And now he just uses variables everywhere in his 6,000 line program. And God forbid one of those 1, 2, 3 variables, God forbid the value was changed from 1 to something else. Can you imagine the troubleshooting that would go into trying to track that down? But you see, you could do that. You could do that because programmers were so cheap. So if it took me a week or even a month to track down a bug in a spaghetti code program, it didn't make any difference. I'm just a cheap programmer. What's important is the performance of the computer. So spaghetti code was the natural evolution of top-down functional decomposition, attempting to maximize computer efficiency and performance. By the way, spaghetti code in hardware looks something like this. I'm sure all of you will recognize this as Doctor Who's original TARDIS. This is a good example of spaghetti code because every piece in here is adjacent to its companion that it needs to communicate with directly. I'm not wordsmithing this very, very well. And so the result of this is everything is kind of all jumbled up for the sake of machine efficiency. Okay. I'm now skipping ahead, 50 years, because now that programmers are very expensive and computers are very cheap, spaghetti code is unacceptable. We don't have the resources to spend a week or a month trying to find a bug buried down deep into some spaghetti code somewhere. And so without going into all the motivations and the rationale behind all of this, we have evolved a different paradigm. Different from what? Different from top-down functional decomposition. And that paradigm is object-oriented programming. So let me answer one of the questions I promised to answer at the start of this. What is object-oriented programming? Object-oriented programming is a collection of tools and techniques which allow computer programs to be structured as a collection of collaborating objects. What does that mean? Well, I'll have some illustrations coming up. What are objects? Objects are encapsulations of related data and the functions which operate on those data. Objects communicate with other objects so as to collaborate in the performance of overall system functions. These three bullet points are the essence of anything that's, quote, object-oriented. Let's go back to this issue of spaghetti code and spending a week to track down a bug. If my system is built as a collection of collaborating objects, and they all have specific purposes and responsibilities, and something breaks in a portion of the system that I can identify, it should be almost trivial to identify the object that contains that bug and then fix that object instead of looking around 6,000 lines of code. This is from the case study book. This is an object model of the elevator control system. And it consolidates all of the code in the system into objects with names like elevator, overweight sensor, arrival panel, destination panel, floor, arrival event, summons panel, etc. Please note, nothing in this object model is top down. There is no, quote, functional decomposition. These objects are all peers. They are peers. Well, let's look at the elevator for a moment. What does the elevator encapsulate as data? Something called an elevator ID, a current direction, a current floor, a current state, and a status direction, whatever that is. And what are the services that operate on those data? Well, those are things like recognize elevator ready, report current status, update direction, update something called floor ready, etc. So if I have a problem that my elevator, for some reason or another, never wants to go to floor 13, I can look at this model and I could, well, I guess the first thing I would say is a button broken in the hardware, the 13th floor button? If it's not, maybe it's not because all the elevators are ignoring floor 13. One place to go to the elevator object. By the way, object models like this also facilitate, this wasn't mentioned on my 3 major bullet points for what is object-oriented programming, but they facilitate overall system design. And that's an area that's no longer in the area of programming, that's in the area of software engineering, and it's the area of object-oriented analysis and design. So I will just tell you, because I didn't mention this at the start, but my co-author Ed Jordan and I taught these various case studies and techniques at seminars literally all over the world, from India China, United States, North America, we had these great programmers and others, students, who were working on these case studies with us. So I have seen in the classroom environment, I have seen many, many different kinds of students approach how to build an elevator control system. And I will tell you that the initial approach that most of these groups take is to create one big object called elevator. And you know they're thinking functional decomposition when elevator now becomes the top of a hierarchy. So if you can imagine doing functional decomposition and call it object-oriented programming, and you make the elevator controller. But actually, after having done this elevator control system with literally hundreds of workshop groups, it turns out that the optimum, air quotes, optimum version of the elevator control system is to keep the elevator object very, very simple and put most of the controlling function into the floor. Because it turns out that floors always know where the elevators are. So if you allow floors to control your elevators, not only do floors know where the elevators are, they know where people are who want elevators. And it turns out to be a much more elegant solution. So that's just kind of a byproduct of using object-oriented techniques. You can also use these techniques at the systems design level to create what I consider to be much more elegant solutions. Okay, so why object-oriented programming? Well, object-oriented programming facilitates reuse. You see, each one of these objects can be used independently in other contexts and in other systems. In fact, if you take this elevator control system and you change its orientation from vertical to horizontal, with only a few changes in the model, you've created a control system for a light rail system, where instead of floors, you have stations. Instead of elevators, you've got train cars. And similarly for the other objects. So facilitates reuse in multiple ways. By the way, if you take the elevator control system and you make it three-dimensional, you have the start of air traffic control system. Let's see, facilitates reuse. And it's not merely reuse of code, but it's reuse of intellectual product, such as business rules and processing procedures and control algorithms. If you have some special algorithms that control some kind of machinery and you encapsulate them and put them into an object, then when you change the machine, you don't have to change your whole system. You just change the controlling object. Okay, let us see what else. Object-oriented programming facilitates system maintenance and enhancement. And the reason for that is that a well-designed object-oriented model, when systems break, they tend to break along object lines. So I've alluded to this earlier, makes troubleshooting that much easier. And I've already talked about this, object-oriented programming facilitates new system development. But ultimately, object-oriented programming makes programmers more efficient. Programmers write code once, turns into an object. That object is in a library. That programmer's intellectual product is reused over and over and over and over again. But there is such a thing as bad object-oriented programming, and I'm not going to go into this. We call that ravioli code, and that's the topic for a whole other lecture. So thank you so much for, I will open up for some questions or comments. Thank you so much for listening to me blather on today.